Hello, good evening.
Good evening, sir.
Good evening. So today we'll cover week 8, which is extended part of probability. That what is conditional probability? Then in conditional probability there are uh, joint probability and marginal probability. Then there is law of total law of probability, and then finally we will have Bayes rule. Okay, so we'll cover that. Let me share my screen. Okay. So okay, we can start, right? Mm, fine. So before we start, uh, hello.
Yes, sir.
Okay, thank you. Okay. So, so there is one thing which is called disjoint events, right? So I'll just brief about this because we'll use this today also. You would have gone through it in previous week lecture. So when two events are there and there is no common event in between them, right? So let's say if I draw the Venn diagram, you can say this is A and this is B, and there is nothing common in between, right? So if it would have been like this, then this is not a disjoint event, but this is a disjoint event. Okay. So basically, what you can say is probability A intersection B is 0, right? So there is nothing common in between event A and event B. Okay. So these are disjoint events. Um, okay. Then there is called something called exhaustive events. Okay. This might not have been there previously, but what does this mean is that if you write um, all the events, all the elements of a sample space are all are covered with events, then you can call that this is exhaustive event. Let's say we roll a die, okay, and let's say you write 1, 2, 3, 4 as the event. Okay, so this is the event. And let's say E2 is there. You write there's a 1, 2, 3 something, right? So this is not exhaustive event. So if you add, let's say, probability of E1 plus probability of E2, right? Uh, Something like this. Then you'll realize that you'll not come across all the elements of this sample, right? So rolling a dice will have 1, 2, 3, 4, 5, and 6, right? This will 5 and 6 will not occur, right? Even though you can see maximum we can have is 1, 2, 4. So these are not exhaustive events. Um, Exhaustive events are something which cause all of them, right? So it has to be something like uh, something like, say, E1 is this and E2 is 5, 6, then it will become exhaustive. So if you combine both of them, you'll have the complete set. Now, are there any common in between or not? That is a different thing. But if they cover all of them, that's exhaustive events. Okay. Uh, Now let's see. One important point is what is independent events. Okay, and if they are not independent, then of course they are dependent events, right? So let me give you just the intuition of this. What is independent event? Then we'll go into mathematics of it. So let's say um, uh, a student is there. Okay, he writes the exam. Okay, he writes the exam. Now, let's say if I tell you that he will pass the exam with 0.45%, 0.5 probability, and he will fail exam with 0.5 uh, thing, right? So this is what I have given to you. And then let's say if I tell you that this student uh, is studying more than most of the student, right? Average more than average student. So like basically you can say studies more. Okay. So can you so this is passing and this is failing. Does studying more impact passing the exam or not? If you come across this question, we'll not solve it. I'm just giving you intuition. So we'll see mathematically later on. But uh, so if he studies more, he's more likely to pass, right? Uh, Something. So it will impact the event, right? Now, if I say he um, uh, let's say he he's not he's which doesn't impact exam, right? Let's say he goes to the class first, right? He reaches to the exam center first. If I give you this uh, date information, will it affect his passing the exam or not? Probably not, right? Because
No,
these are
sir.
independent events. You can say reaching the center first and passing the exam has nothing in between, right? Common or something. So if something affects what is going to happen next, we call them um, not independent, right? Not independent. So this first is, you can say, independent event, and we'll see what is that uh, and little bit more, right? So first, let's start with this conditional probability part, a joint probability, margin probability. Then I'll come across this again, but just so I give you the intuition that independent events are something which happens, something happens that will not affect what will happen next, right? So let's say uh, event A happened, right? It happened already. It will not affect in any way to the next event, right? Which is going to happen due to this, right? Let's say rain happened and I couldn't able to reach the class, or there was no train, so that this happened, right? So something happened earlier, that's why it will affect the next whatever going to happen, right? So this cases are not independent if like this. But if happening something will not affect at all to the next event, are called independent event. Okay, this intuition will solve it mathematically, but before that we need to learn about this conditional probability and all. Then I'll prove that. Okay, fine. mm, okay, let's see. So okay, so this is the task. So yeah, we want to distinguish between independent and dependent events. So you just got the intuition, but we need this conditional probability to prove it. Okay, so let's do this. Let's learn about the conditional probability. So um okay, so you would have seen this, right, in week 4, I guess, that we had relative frequencies, which in which case we wrote like this. Let's say somebody's owning a smartphone or not, right? So that's what we'll write here. This is from the survey. And what is his gender, right? So gender is written here, and owning a smartphone is here. And based on that, we divided our data like this, right? So this is relative frequency, and then we call, let's say, this as a row relative frequency, and like this both, and then this are called column relative frequencies, right? So uh, we'll uh, now what we actually did is, um, since we are dividing each by 100, because we are doing that because the total is 100. Okay, if it had been different number, we would have done that. So if it was, let's say, 120, 140, then this whatever this numbers are coming up, we would have divided by that number, right? To get the probability. Like, how do we write probabilities? Favorable outcomes divided by total outcomes. So uh, currently I have total as 100, that's why I'm dividing it by 100. And this is very simple scenario, so we'll have all the probabilities, right? So you can say kind of that this all could be probability, right? So if we solve, let's say, what is the probability of let's say a probability of picking a female. Let's say I want to do that. Okay, so what is going to be that? So I'll write total people, right, who gave the survey, which is 100, and
44 by 100.
females are 44, right? So that's how I get this, right? And if I ask you for male, we'll get 56 by 100. Same way you can find for, let's say, owning a smartphone. How many owns a smartphone? Probability of owns a smartphone, right? So we will write that using this column, right? So just that I have to see, and total are 100. So 100 people were surveyed and 76 are there, right? So this way I can find the probability, and you can see the same thing will get here using this. So if I do 76 by 100, it's going to be 0.76 here, right? This one. And now from this conditional table, we are interested in this, but we are more interested if two things are happening together, and then what is the probability, right? It will change the probability. So let's say it's given to you, okay, here. Let's say it's given to you that whoever we are picking, let's say does he or she owns a smartphone. um, if I tell you that we are going to select only female, right? So if I ask you how many uh, females have smartphone, right? How many females have smartphone? Then what will you do? You will choose females first. How many females, right? So total in this case will change.
34 by 44.
Right? Probability of female owns smartphone, right? Smartphone. So in this case, what will change is we will first write that I want to check how many females are there, right? 44. Then how many of this 44 are owning smartphone? 34, right? So this how I'll get probability of this, right? You're kind of seeing that this, okay, same thing we studied with relative frequency, relative, yes, same thing. That's what this is coming from. Okay, that's why we do that part. Why we do that is, uh, so in and then we get this probability, right? So see, now there are four kind of questions you can ask. One is this, which is female and not owning a smartphone, right? So this one question. Another question, female, yes, and owns a smartphone, right? Let's say yes, right? Another question you can ask is, he's a male and not owning a smartphone. And final one is male, and yes, he owns a smartphone, right? So this four questions we asked just now, right? These are called joint probability. So now we are joining, right? So joint means we are joining two things like female and due to this and we are joining. Okay, so this and we are using to join them, and by making that we call this as joint probabilities. Okay, if we uh, if we look at row wise, let's say like this, okay, this whole thing, then it will become marginal probabilities. Even if we look at column wise, okay, then also it will become uh, a margin probability, right? So if we can see what kind of marginal probabilities, probability of female, right? This part, probability of female, this is a marginal probability. If I ask you what is probability of male, this is also marginal probability. If I ask you what is probability of owning a smartphone, that is also marginal, and this guy is also marginal, right? So this four type of marginal probabilities are there in this question. Okay, and this four type of which are inside this are joint probabilities. Okay, so here we are not uh, taking two of anything, right? We are just taking one portion of it. Female, is uh, she a female? Whoever we pick up, is she a female? So that is the question, correct? And is does anyone, right, any person owns a smartphone? Then we figure out that probability, right? So this is marginal probability.
Sir,
Yes.
sir, my problem in it conditional probability. So sir, how to use this table for conditional one? Because sir, how मतलब which one data we have to take as denominator and which one data take as numerator?
So
So sir, this
that
is confusing.
yeah, no issues. So we'll cover that. So next is conditional probabilities and same thing, right? So depends on question what you have to take as a uh, kind of say let's say denominator. Okay. So see questions. Yeah. So let's say question is let's go a little bit more. Yeah. So
Awesome.
yeah. So let's say this question, right? So among female buyers, what is the chance that someone owns a smartphone, right? So see now we are saying that we know that somebody is there. Uh, the person is female, right? We know that, correct? And we want to see out of female, somebody owns a smartphone or not. We don't care about male here, right? For this question, let's say among people who don't own smartphone, how many are male? In this case, first I need to check how many don't own the smartphone, right? So that part I have to check first. Not owning, right? Then next question is he a male or not, right? That is my next thing, right? So first in this case what I did is I chose female. Among female, then what is chance that somebody will own a smartphone, right? So it's uh, it's not other way around. See, they're not asking if somebody is not owning smartphone, is she a female? That is not the question, right? This first one is uh, but they are saying that we know that the person selected is a female. Now, does she owns a smartphone, right? Someone owns a smartphone, right? So owns, right? Here, let's say owns. This is not the question that how many owns
Sir,
a
the
smartphone.
question, sir, the question that you cut is we will discuss in base theorem. No?
I don't know. You can do here itself. Doesn't matter for now. You can solve both questions. Depends on. See, here we have data is given, right? We
Yes.
use base theorem because something is not given to us. Let's say something is this is not given. Then based on that, that question will appear. But here we have all the things, so
Yes.
no need to worry. Okay, we can solve any way around for now. Okay. So let's see. Smartphone and female. Yeah. Mm, okay. Uh, okay. So see, conditional probabilities. We denote it like this: probability of some event, right, will happen given that already the another event has happened, right? So this, which is after this, you can say slash or horizontal vertical line. Uh, this f is already happened, right? So this happened.
Sir means in the first event of F, how many chances of happening event E?
Yes. So already f has happened, and then so here see the comes the picture that let's say this is E, this is F. Okay. Now they are asking that event F has already happened, right? So this happened. Now what will be the chance that E will happen, right? So you know that if F has happened, then there is this much portion. Uh, can you mute? Uh, can you mute whoever is speaking back? Okay, thank you. Okay, so see uh, this portion, right? This portion is only left, right? E and F both can happen here only, right? E and F both can happen there only, and F, correct? So since we were given that F has already happened, now we wanted to figure out the probability, right? So it will um, kind of say you can say affect the next probability, right? So happening of E. Earlier we didn't know that F has already happened. That's what we are doing previously, right? Before today's lecture. But now the question is, already something has happened. How it will affect the next, or happening something which should have happened together, correct? Something like that. So you can say, like, let's say in exam we take, right? So somebody studies, he might pass, right? That's how it affects. And let's say reaching a center first will not affect, right? So if they are not um, dependent on that, then you can say it will not affect much. But here, don't worry about that. We'll go that independent part. But uh, here in this question, if you can see, um, how many among female buyers, what is the chance that someone owns a smartphone, right? So first we need to see how many females are there, right? Then in that, the question is how many owns a smartphone, which is 34, right? So from this we know that own smartphone and female, right? Something like this. Given that she is a female, right? The person selected is female. Given this, does that person owns a smartphone? So this is how you will write, which you can, for now, let's say 44 is the total and 34 is the favorable outcome, right? Okay, like this. Female and female doesn't own or own. Someone owns,
Owns a phone.
yeah, owns a phone, right? So among female, what is chance someone owns a phone? Yeah, correct. Mm,
There is a misprint.
yeah, I think so, right? So there could be a mistake. Yeah, let it be there. So this is different question actually. So female and the not owning a smartphone, right? So you can say this. Uh, then you have to choose this one, right? Female and not owning a smartphone, which is this, right? But the question is female and owning a smartphone. So we did that. Okay, then mm, okay, no issues. So let's see. The next question was, what is the probability that uh, somebody who it's given to us that he or she doesn't owns the smartphone, right? This is given to us. Now, whether he is going to mail or not, that is something we have to figure it out, right? Given this is given to us that somebody is there who doesn't own a smartphone. He's Is he going to be a male? So that we want to figure out. So what we'll do is we will again do that. We'll take common of both of them, right? So male and uh, you know doesn't own, right? This common thing we have to figure it out, and we have to divide by uh, doesn't own a smartphone, right?
Yes, sir.
Doesn't own. So you can see, let's say I have this two, right? Let's say um, one is, let's say, male, and this is uh, doesn't own. Okay, uh, this two. Then they are saying that take this common and divide by the whole thing, right? So this, if I, let's say, choose color, then you have to actually choose the whole thing, right? This whole red part, which is doesn't own. That's how you will get this probability. Okay, so if we see how many doesn't own is, there are 24 people who doesn't own it, right? And out of that, there are 14 males are there, right? Which are common, or you can say not owning and male, right? So this you will get 14 who are male and doesn't own it, and 24 are total people out of 100 we who doesn't own, right? So this changed our probability. So earlier what happened is, let's say if I ask you, how many males are not owning a smartphone, right? That was the question. Then you would have done 14 by 100. This is just the probability. But here this is conditional probability. Condition is that we know somehow that
He doesn't own a
uh,
smartphone.
doesn't own a smartphone. This is given to us. So this will reduce our sample size, right? Let's say, or yeah, sample size. It will reduce, right? So previously we would have taken the whole thing, 100 of them, but now we don't need to take 100 of them. We just need this 24 because it's given to us that uh, that guy doesn't owns the smartphone. Now find the male. Okay, so this is what is so basically here the idea is that if it is just the um, yeah, just this insight thing, right? So this four thing are joint probabilities. Okay, and this all are called marginal probabilities. Okay, so basically knowing what is joint probability, what is marginal probability, most likely will not help anywhere in question solving because you most likely never figured out, or you most likely don't have this table. But if table is there, then yes, you can do that. Okay, if table is not there, then if it's just a question, then it becomes really difficult that what is what, right? So uh, don't worry, you just need to know how to solve this kind of question. Then we'll see how, if question comes up which are in words mostly, then how you'll do it, right? So we'll need something for that. So then it will mention, is it independent, dependent, are they disjoint events, right? Mutually exclusive basically, um, or they are exhaustive. Everything will be given, and then we have to figure it out the probability, right? So let's see.
So you are not audible.
Yeah, give me. Okay, okay. Let's say so. So now what we'll do is we'll do what is independent and not independent events, right? Or you can say dependent events. We just saw the intuition, but now we can actually define it. So so say it easily, what is it? So P, some event A is there, um, intersection B, right? So this I want to figure it out, and if I say it's equal to P of A multiplied by P of B, then they are independent events. Okay, if this becomes equal, then they are independent. Okay.
So that means there is no common thing between A and B.
Yes, you can say that, yes. So if this is equal to this, then uh, no common thing, or no, that doesn't mean that there is no common thing. It could be common, but happening one thing will not affect the other one. Okay. Uh, so let's say A is there, B is there, right? So there is common in between. That is what we are figuring out. That's what this part is, right? Uh, Intersection part. But since they are not affecting each other, we can directly figure out this A intersection B with probability of A happening multiply by P of probability of P happening. Uh, so uh, there could be common thing. Okay, it's not like there is nothing common. Independent means let's say A happened will not affect any way in happening of B, and so B happened, then it will not affect in any way of happening of A, right? So let's take an example, then maybe it would be quite clear. So let's say
Sir, but how can it be, sir, possible? Probability of A intersection B is,
yes, yes,
it's
tell me,
not clear.
sorry.
Sir, probability of A intersection B equal to probability of A and probability of B. But
Yes,
sir, there is some common point in between them, na?
yes, it
So,
is there.
if we multiply both of them, then the commons will be multiplied 2 times.
Multiplied 2 times. Multiplied 2 times. No, that is multiplication doesn't happen like that, right? Addition is different thing. In addition, it might add the other part, but multiplication is uh, no, right? They will happen together only. Um, okay, let's take the example. Let's say we have this dice which we are
Sir,
going to roll twice. Yes.
sir, if you have any formula sheet for stats from week honors week is 7, then you can provide us, because from week 7 the formulas is quite confusing, sir.
Mm, okay. So
Yes, sir.
formulas are quite confusing. Okay, I'm not sure about that. We'll see. Okay. Um. Okay,
So
let's
how
see
we can
this.
find the
What
intersection of A union B? Is that
A
any
union
formula for?
A
Yeah,
union B is different. A
A
intersection B is
union B.
different.
Sorry, A union B complement.
A union B complement, that you can figure out. So before that, you need to know this independent dependent case. After that, it will come.
Oh, okay, sir.
Yes. Let's see this example. So okay, so further that first roll of dice is lands on 4. Okay, so this example says that first is like first dice roll a 4, right? So you did toast it twice, then first one rolled 4, right? And so that is my event first, like you can say E, that first roll is 4, right? And then F is um, given, but this is like, okay, given this information, so they are saying that given E is given to us, then this F happens something which is like, what is the resulting probability that sum is going to be 10? Sum is going to be 10. Okay, so this we wanted to figure it out, and you can see we can write of sample space, all of them, right? Let's say 4 1, because initially 4 E we got, right? That 4. Now what can happen in second die? Anything can come up, right? 1 to 6. Now now they're asking us find the probability that sum is going to be 10, right? So in all this 6 scenarios, only one way to get 10, which is this 4 by 10. Sorry, 4 comma 6, right? Because initially we got 4. If 6 comes in second row, then only I'll get 10, right? So, uh, right. So you can write probability as this 1 by 6 given f. Okay, this part actually I think we were doing independent multiplication. Okay, so see, now this is multiplication rule, right? So don't get confused. This all are names, which most likely even I don't recall them name wise, but when the question comes, what needs to be applied, that you should be sure of, because nobody is going to tell you that here multiplication rule will be applied, here this rule will be there, right? So based on the question, you have to figure out the probability, and you should know what you have to do: multiply, divide, or is it a conditional probability? Should you reduce the sample size, right? So this all you have to think, right? And then you can solve it. So uh, kind of thing, right? So this is what being known to us, that p of e intersection f is this, right? And then what you can do is you can actually expand this. So p intersection f is equal to, you can bring it here, or maybe you can multiply both the side with p of f, and you'll get this, right? So we did addition rule, which was p of let's say e union f, then it would have been p of e plus p of f minus p of e intersection f, right? This was addition rule. This is multiplication rule. Okay. And you can actually have this p of e intersection f here also, like this guy can come here, right, if needed. So if something is given such a way that I know f has already happened, now find the probability of e, or something like this, then maybe you might need to use this. Okay. uh, uh, let's take this example uh, to solve this using multiplication rule. But remember, we don't uh, know when multiplication rule is gonna come, right? So let's just not think about multiplication rule. Why I knew that this is multiplication rule, that will talk, and then we can solve it, right? So also this is the question. In an introductory statistics class of 40 students, right? So 40 students are there. The number of males is equal to 23, right? So 23 are male and 17 female are there, right? 17. Two students are selected at random. Okay, two students are selected at random, so we have to select one and second student, right? The first student selected is not returned to the class, so whoever gets selected will not be returned to the class.
Sir,
Yes,
sir, one question, sir. What is mean by the sampling is without replacement?
that's what it is, right? So I select one student out of this 40 student. Okay,
Yes.
I
Yes.
select one. Then how many left here in class?
39.
39. So
Yes.
if I send him back, that will make it 40. Then I'm not. Then I'm not. I'm doing what I'm doing is with replacement. Okay, so initially 40 were there. Again, it became 40. But that's not my target. My target is I should select one, so that will leave 39, and then I will again select one, right? So that will leave 38 in class, and two were selected, correct?
Oh, okay, sir. Understood.
So yes, that is with without replacement. Okay, so when we do replacement, the initial number will not change. But if you do without replacement, then initial number will change. So initially, let's say 40 were there, 39, 38, 37, and so on. Okay, if you go more than this. Okay, so we have to choose 2 students in this, and it's being said that they will not return back to the class. Okay, that's sampling without replacement. That's what it is. As I told you that first student selected is female and second is male, right? So that's what we want to do is first should be female and the second should be male. That's what the question is. Um, and actually you can solve it easily. Let's say I wanted to select female, right? Of, and then that should be first. So order does matter here. Like I can't do this and this and then multiply, right? Because here whatever I do first will affect my uh, next task, right? So I have to choose a female out of 40 students. So how many females are there that I can choose?
17.
17, right? So yes, so I selected first of my 2 students, right? So out of 2 students, I selected my first one. Now how many students left?
39.
Yes, and out of that I have to select what? Male, right? So how many are total? 39 left, and of that I'll select a male, which are 23,
23.
right?
23.
So selection of first student did it affect my second thing? Yes, right? If it was with replacement, then what I would have done is, let's say first student was chosen as female, and then second student was
23
selected
by
as
40.
male, right? Nothing would have changed. Even let's say first student was selected as female, and then let's say second with replacement I'm choosing as a female, second as female, then also I would have got again 40, right? It would have not any impact on my thing because it is with replacement, which we generally don't do, right? We will always, like this kind of question, like selecting someone, we always do without replacement, right? Students kind of thing, humans we select. So this is how you can do it. And then how do you know that you have to multiply or you have to add? Do you have to multiply or add? How will you know this? Because I did it.
We have to multiply because we have to
It's
find out total
happening
probability.
simultaneously.
Yes,
It's
right?
happening
So
simultaneously. We're doing it just after the another.
yeah,
Sir
so
means it is
we are,
like permutation.
yeah, you can say that. uh kind of that is only, but when we find probability, we always divide it by total outcome. That's all. Otherwise, that's why we study permutation before this. And we have to use multiplication because we'll do this and second, right? So whenever and is there, we do multiplication. You can
Sir,
move on
not
then.
39, sir, 40.
Where?
23 by 40.
No,
Yes,
no,
sir.
this is 39 only because we selected one guy, right? One girl is selected, female student is selected. Initially 40 were there,
Hmm.
correct?
Hmm.
Then one is left. So how many students I have now after one got selected? 39, correct?
Oh, one is already selected.
Yes, that's what it is, right? So first student selected, not returned to class. So I can't send him back, right? So how many are left? 39 only left,
Yeah.
right? So
Hmm.
this, okay. Let's see what is going to be if my first student is female and second is also female. Okay, the second female, second is also female. Then what will you do? How will you figure this out?
Sir, first
17 by 40 and 16 by 39.
16 by 39, right? So that's how the 39 is coming. It has uh right, maybe this got confused that all of them are not changing, but why this only person is changing? But since we already selected one out of that, we have to see what are favorable cases left, right? So that's why this is our question. Let's say we want to select first as male and second also male. Then how will you do it?
23 by 40 and then 22
Uh,
by 39.
equal 2 by 39.
Correct? So this is how you will figure it out. So this is what multiplication rule is. Um, multiplication rule, how did it happen is, see, it was uh, P of E intersection F is equal to P of E. Then what we'll do is, or P of F, let's say we'll go with this only. P of E happening given F, right? So given F is there, then you wanted to figure it out, right? So what is my you can say F in this in our scenario, which has already happened. What happened first? We selected female student first, right? Female student selection. This is my F. Okay, and experiment. Mm, okay. First one female and second male. So this I yes, okay. And E intersection F is student selected. First student selected is female and second is male, right? So first female and second, and so this way this intersection is there, and second male, right? So we need to figure out one more thing, which is this, that female student is already selected, right? Female student is already selected. Now what is the probability of selecting a male student, right? So this is what that condition is, and that's what we did. We wrote P of F as 17 by 40, and then we multiplied by, we already know that female was selected, so 39 left, and now selecting male would going to be 23, right? So this is this and here, and due to that we were able to figure out this person, right? P of E intersection F. So that's what multiplication rule is. Okay.
Sir,
Yes.
so in this one, when we are selecting males, we'll be taking it from the total males. Now, why we are including the whole class?
We are selecting from whole class, not just males, because we have, so first we have females out of whole class, right? We have to select two students. See, the question is, select two students at random from the class. That is my question. You have to select two students out of random. Now they are saying that if you do this, what is probability? Probability that first student is selected as female and second is male. That is the question. So many scenarios could have happened. Two students, you can select both male, both female, male, female, female, male, right? First and second, this all four orders. But they are giving us one of that way, that first was selected female and second was male. So in that, how will you do it? So this is how you do it. First, you'll see how to select a female. Then, since female was chosen, how to select a male out of the whole class. Right?
So then when we are selecting female, then we from the
No,
whole class, the probability of getting female will be only possible with the female population that we have now.
that we don't see. Initially, we didn't know that the selected student is going to end up as female. What we know is we selected two students. Now they are asking after selection that, or you can say selection will happen differently. Then the question is, what is probability that first was chosen female and second was male? Okay. So you can choose in four ways, right? Three and four. Let's say female, 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 male, male, female, and male, male, right? So this four way you can do it. But they are saying that what is probably that this way it will happen. That you have to figure it out.
Okay. We have to just get out the probability of getting female out of the whole class.
Yes.
That's it. Okay.
Yes. Right. So, yeah. Okay. So there's something called generalization of multiplication rule. So now we had only 2 events, right? But what will happen if you have more than 2 events? Then what you can do? What you can do is actually will not prove it. You can just remember it. That let's say we have several of this them intersection, right? P of E1 intersecting with E2 with E3 and so on. Then how will you figure out this probability? I mean, generally we don't have this huge question. Let's say 3 or 4 could appear, right? Um, then how will you actually do this? So what you will do is you first you'll figure out how E happened, right? So let's say E happened as a female, selecting first female, right? Maybe let's say 17 by 40. Then next question is second also should be female. Then what will you do? 16 by 40. Then let's say third is male of the sorry not 40 39 male of third was chosen as male, so male were 23, right? So 23 out of 38 because already 2 got selected, 1 2 3, right? Now 37 left, and if I ask you what is fourth was selected female, then how will you do it? 20 how many others?
15 by
15
15 by
15 by
37.
37, right? So this also so what I'm doing is I kind of did E1 intersection E2 in this case. Okay, I included both of them. Correct. Here also I included all 3 of them: E1 intersection E2 intersection E3, um, and yes, this 3, right? So this 3 already happened. Then what will be the probability of happening? Something, right? So this multiplication rule you can generalize for more of this event. So formula wise it goes like this. Okay, so E1 has already happened. Then how E1 which already happened affect E2? Then both of them already happened. Then how will it will affect E3? Then several of them happen. Then how will it affect my En, right? So that's what it is. And you can see you just have to multiply all of them and you will get the answer, right? Um, okay. Mm, let's do this question. Okay, so you get the idea, right? So we'll go to independent dependent case.
Sir, my question in activity 8.1.
Okay, we'll cover that later. Okay, after
Okay, sir.
let me complete this. I'll cover that. Okay, so now we are into the see, this is very important. What is independent and what is dependent event? Okay, because if you know this part, then most of the questions you can solve easily. Okay, so will the conditional probability that E occurs? So something has occurred already, right? Uh, occurs given that F has occurred can generally be equal to unconditional so basically be equal to generally unconditional this the sentence means, so let's say P of E occurred and P of F occurred, right? So this is it equal to P of E multiplication of P of F? Is it like, is this the scenario? And we saw just now, right? No, that is not the case. What E and F is intersection of F. In this case, actually it is P of, let's say maybe you can write F or E, doesn't matter, F, and given that P of F has already happened, then figure out the P of E, right? That's what this multiplication rule told us, right? So will the conditional probability that E occurs, given that F has already occurred, is equal to unconditional probability of E. So is it equal to P of F into P of E? This is my question. And an answer is no, right? Not in all the cases, but somewhere it is yes, right? Not all the case, but somewhere it could be true. So what is that somewhere? That somewhere is um,
When they're
where
independent.
when yeah. So in this case, when E F is equal to actual E, and this is what is independent. Okay? So let's say E given F is equal to actually P of E. I mean, F didn't have any impact on E happening, right? So what earlier we did is we selected a student, a female, that would have affected the next outcome, which is choosing male, right? Um, but if we would have done with replacement, then it wouldn't have affected, right? So with replacement, let's say I choose first female, then it's going to 17 by 40. Then with replacement, right? So again it became 40. Now I'll choose anything, just a male, same thing. Again I replace it and then choose. From 40 I can choose anything, let's say 17. It will not change at all, right? Any number of people I can, like any number of I can go, and it will not affect at all. So this are actually independent events. Something happening will not affect the next outcome, but generally that's how it doesn't work. We do something and it will affect the next outcome, right? So that's where you will need this independent and dependent events, right? So if they're independent, then it's good. But they're dependent, then you have to use the multiplication rule one, okay? Not this one. Um, not this one. This will only work if they are independent. So you have to check independence check you have to do. Then you can use this. If they are not independent, then you have to use this. Okay. Yeah. See.
Sir, Bernoulli principle is included in this week or not?
Bernoulli is a random variable. It will come in random variables. So next week could be there or after that.
So, sir, in this week, there is a Bayes theorem.
Bayes theorem, yes.
Bayes theorem.
Yeah, it's that. So that is we'll first cover law of total probability, then Bayes theorem will cover. Okay. Let's see. Okay, I think I explained this. That if they're independent, then mm, see. Just so I let you know that if they are going to be independent, then multiplication will not affect anything, right? So you can write P of F multiplication P of E as well. It has nothing, like just the multiplication. Okay. But when you have given something, right, then it will affect. So did P happen first and then ask of F, right? So I mean, what I mean is that's a P intersection F is asked, and you are figuring out P of E into P of uh, E, and F has already happened. Is and then another thing you can do is that's a P of F, given that uh, E has already happened, right? So in this case, E happened already. In this case, F happened already. But see, here it doesn't have any impact, this formula, right, of this. But in this case, it's this two are not equal. Okay, this is not equal to given E. Okay, this is not equal because we are multiplying also different entity, right? So to get the same answer, we'll come to same answer. That is not the issue, intersection part. But this values are not equal, and then this P of E and F is also are also not going to be equal, right? They are also not going to be equal. So here they are both equal, this multiplication you do anyway will not affect anything, and you'll always come up with this P of E intersection M, and this is the scenario when they are independent. So if they are not independent, then you have to be a little bit careful that what should I do first? Should I what is given to me? F is given, then I have to figure out E, or something else. It's vice versa. Okay. Yeah. So in any question, if it's being asked, E and F are given, are they independent? How will you check the independence? How
We
will
see
you
the
do that?
dependency of the both events that are happening.
Yes.
The logical reasoning, maybe, kind of where the logic fits.
So I generally recommend don't go logically. With independent events specifically, don't go logically, but go mathematically. Most likely, because we don't know is are they are going to be independent or not. But if you use this formula, which is E intersection F is equal to P of E multiply P of F, if you do this, and if they both come up equal, then you know that they are independent event. So most likely all three of them will be known to you. Okay, when you check this independence, or you need to check the independence.
Okay, then we don't have to check for the logics.
Yes, if in case of independence events, because you'll not know when it's going wrong. But if you use this formula, then we are sure that they are independent event. Okay. I think
Sir, one more formula we know that P of A intersection B equal to P of B into P of A minus B.
P of A minus B. Sorry, what is that?
P of A intersection B equal to P of B into P of A minus B.
I'll write. So can you P of sorry, I was somewhere. It's P of
A intersection
plus
B
intersection B. Okay.
equal to
Is
P of A into
yeah, that is there. So P of
hmm.
B, then minus P of A
No, no,
union
no,
B.
no, no, not that one, sir. P of
Sorry,
B
then
into P of A minus B.
plus, but plus is there.
Oh,
Addition is
sir.
there.
Addition is there.
Okay, then P of we are saying P of
Yes,
B
oh, sir,
given.
it is for any particular question, I think. I didn't remember.
Uh,
Hmm. Most
there's
probably
no such
party.
formula. But
Okay,
there's no
okay.
such formula. There are two formula, which is addition rule, multiplication rule. This is multiplication. Addition is the other one. Um, A intersection B subtraction. I'm just looking for another like example which can give you. there is a question on this. So okay, there are no. Maybe we'll see next, like next thing, and then could be there. So question will be there which requires independent. Dependent. Yeah, there is example in this. Okay. Okay, so yeah, this is this rolling a dice question which we can do. From this, you might get an idea of what is independent dependent event. So we roll dice twice, right? So we have this dice. We are going to roll them twice, and we're going to write their outcome. So this is sample space, right? You have to write all the elements of that. Then we define some events. So first is the first outcome is 3, right? So where is it? This is the first outcome is 3. Correct? Then sum of the outcome is 8. So sum of the outcome should be 8. Is going to be, let's say, 2, 6. Then this one, right? So this is the second event. And then sum of outcome is 7, which is going to be here, the diagonal. You can see, right? So this 3 kind of events are given to me. Now question I can see from this is, right, that maybe given to us is even are even and E2 independent. Okay, so first let's see, are even and E2 going to be independent? So how will we check independence? P of E1 intersection E2 is equal to P of E1, and I will multiply by P of E2, right? So this I'll do, and if they are going to be equal, then I'll say they are independent. Okay, so let's see. So we can do that. So first outcome is 3, right? And what is the probability of this? 6 by 36, correct? This all thing. First outcome is 3. Sum of the outcome is 8, which is here. And if you count them 1, 2, 3, 4, 5, 5 out of 36 scenarios are there where this is happening, correct? Now they are asking what is E1 and E2, right? So E1 has to happen, means first has to come 3, and then summation has to be 8, which is only possible at one scenario, correct? So that is 1 by 36, this E1 intersection E2. Now what is my E1? E1 is 6 by 36. What is my E2? E2 is 5 by 36. Are they going to be same? Not likely. So they are, sum of the outcome is 8. So 2, 6, 1 by 6, and then first is 3 and sum 8. Yeah. So they are not independent. Now let's see, is E1 and E3 are independent. So we can see E1 is going to be 6 by 36. You already know. What is 7? Sum of 7. sum of 7 will get here, right? This one, which is 6 by 36 again. And where we'll get summation is 7, only one case, correct? Which is 1 by 36. Uh, yeah, only one scenario where we'll have E1 intersection E3 as outcome, right? So first we got 3 and then some got 7.
Sir,
So here we got
this is independent.
this is independent, right?
Understood, sir.
Independent. So from this we can see that, see, here's same question was there, sum of outcome is 8. Here sum of outcome is 7. But since now both the side it's equal, we kind of say that they are independent. This scenario coming of 3 and some outcome is 7, but in this case it's not independent, right? Solution, same thing, and we did multiplication and they are not in equal, right? So that's how we check the independence. Check of independence is only one thing you have to remember, that you have to use this this rule, right? This should have to be equal. Okay. And same thing we'll do with the another scenario where we'll get summation this is equal, and then we'll say that they are independent. Okay, so E1 and E3 are independent, and E1 and E2 are not independent. So they look like same thing, like let's say some summation only, but they are not. Okay. Mm, let's see if we can do this. Consider again the experiment of randomly selecting one card from deck of 52. Okay, you have to select one card. Okay, so one thing is when we select one card, uh, go there. Okay, let's see. What is even a face card is selected, right? So how you can select a face card? This always, right? This always are selecting face card out of 52. So how many are there? 3 into 4, 12, right? So selecting face card is this. A king is selected. That is my event 2. So how many ways we can select king is 4, right?
Sir,
Yes.
sir, what is mean by ace card? ACE card.
Ace is this. This is
Sir,
ace.
means if first of row of spades, diamond, and
No, not first
first
of all.
row.
You know this card, right? This A. The card on which A is written. That is ace.
Oh,
Not first. I mean, how will you call this? A only. A written on the card, which is called ace.
understood, sir.
Yeah, the heart is selected. Okay, so now heart we have to select, right? So how many hearts are there? This many hearts. How many are there? 13. Okay. Now again the question is, we will cover E1 and E2. E1 and E2 independent. Then what will you do? You will multiply both of them, but you need to know this also, right? That intersection, is it going to be what is going to be a face card and a king card, right? So face and king, what's going to be? Um, or you can take intersection of both of them, which is so face are all of them, and intersection is this guy, right? Just the king, which is 4 by 52. Okay. Okay. Now what is even, which is 12 by 52, and then we have again 4 by 52. King is selected, right? So from this we know that they are not independent. Is that the question? Yeah. And they are not independent, right? So same thing, that's what being explained here. but that's what it means. Okay, that we have to pick all the kings and they should be face cards, right? So this is just a subset of the whole set. This 12. Out of that 12, this four are there, right? Um, and they are not independent. Now a face card is selected and a heart is selected. Now what it's going to be? E1 intersection E3. So if we see what is going to be the common between face and heart? How many are there? If I draw this three, right? Face as well as heart, correct? So face as well as heart are going to be 3 out of all the 52 cards. And P of E1 is P of E1 from here I can write 12 by 52, and I have to write P of E3 which is 13 by 52, and they don't look like equal to me because here we have 7 by 4, then they are okay. Sorry, they didn't, but they are 3 are 50. So this is actually independent case. Uh, I I would have missed it. Okay, so E1 E3 are independent, but E1 E2 are not independent, and they here went on to E2 and E3 are independent or not. We can do that. Let's do E2 and E3 one, and we can check also. So E2 is a king selected. King can be selected in 4 ways, right? 4 by 52. Heart is selected. Heart can be selected 13 ways out of 52. Now king as well as heart. Heart of king. How many ways you can do that? Heart of king, 1 way out of all the 52. So if you do this, then you know that 13 into 4 is actually 52. So yes, they are also independent. Selecting king and heart. And you can see they are independent. So whenever the question is check the independence, you have to do this, right? You have to do this. You can't follow your intuition. Otherwise, you might end up having incorrect answer. Okay. Now, I think the next idea is how do we kind of expand the properties of this. Okay, so the next is we have E and F events, E and F, which are actually independent. Now the question is, are E and F complement? So F complement is opposite of F, right? Are they going to be independent? My question. We can prove that. So just let you know that if this is F, right? This is F, then whatever is outside of F is F complement. Okay, so this everything is F complement. Okay. Let's use. So let's say we have E and F. Okay. Now the question is, what is common in between E of E intersection? I'll take F of complement, right? So what is common in between E and F complement? So you know that F complement is going to be all of this, right? Outside of F. So not this maybe, but outside of F, whatever comes is F. Okay, so this E is there. Everything is F complement, right? and we are asking what is common in E and F complement. So you can see this portion, right? This um let's say not color. So this portion, right? This this portion you can see is going to be common in between, correct? Okay, fine. This is the one I want to figure it out. So are they going to be independent or not? So basically what I'm asking is I am asking is this is going to be equal to P of E multiplied by P of F complement. Is it going to be? So proving is okay, we can okay, proof starts like this. So let's say this was my Venn diagram, and I want to figure out what is this, right? P of this is P of E, and it is common with F complement. This is what I want to find out. And the proof of this starts like this, right? So what we do is first we start writing what is P of E. So we know that some portion of P of E is common with F, which is this. So I'll write that. So the common part, and then I'll say the rest is common with F complement, right? So that will I write again. And the next thing I'll do is can expand it. Mhm. Okay, sorry. If I was saying here we reach, right? So let's see. So uh, I know that they are going to be independent, so I can write them as P of E multiplied by P of F. This part I can do this whole thing, right? Then this will again come up here, same thing, P of E intersection F complement, right? And that's what PE is. Now what I will do is I can expand this. Okay. Uh, then mm, okay. So this is This is quite simple, but so next what they are doing is actually they're bringing it to the side. So then you will have 1 minus p of f. Okay? And here this side you will have p of e complement, e intersection f complement, and 1 minus f is actually p of f complement, and this was p of e, and that's how you get that. If you take intersection of f complement, then you'll have this, right? So whatever scenario is, so we have this e and f if they are independent. Okay, if they are independent, then e is actually independent with f complement. Okay, they are also going to be independent. E uh, Another scenario could be that e complement, is it independent of f? Yes, they are also going to be independent. And are both of their complements are going to be independent? Yes, they are also going to be independent, right? So this all four of them are going to be independent. You can prove them, all of them, but this is what we did. Same way you will have this. You can maybe try this. Okay, but so if these two are independent, if this is given, then we can say that anything complement of anyone or both are also going to be independent. Okay. Yes. Okay, so when we have multiple events, right? So let's say EFG, even H, I, any number, then how will you check their independence? Is what you will do is you will first check P of uh this P of E intersection F intersection G is should be equal to this, right? So individual probabilities. That's what it did, right? So intersection F, in this case we had two, so we checked them, P of E into P of F. This is what we did. Now if I have three, I have to check this. On top of that, what I have to do is I have to individually check them. So I have to check this two, then this two, then this two as well. Okay. So E with F, F with G, maybe you can call, or and E with G as well. Okay. So here you can say kind of we have three. We have to check pairwise. So how many we checked? 3C2, right? 3C2, which is equal to 3. So if you have more than three, let's say five of them, E, F, G, H, I. How many conditions you have to check? So actually we did this 3 plus 1. 1 is coming from here. So I have to check this way, that E of E intersection F, intersection G, intersection H, intersection I, that I'll check this my one condition. Then from 5, I'll choose 2 at each time and then check their conditional, are they independent or not, right? So if all of them are independent, the 5C2 is 5 into 4 divided by 2 is going to be 10. So 5C2 is going to 10. So you have to check 10 plus 1, 11 conditions. Then you are sure that this scenario is independent. So all of them are independent, right? This or you can then only you can use this formula. Otherwise, you can't choose this formula, right? Okay. This many are going to be independent. So if more than them are there, then you have to check each individual um, pair, each individual pair, and then you have to compare them. And then if this comes out, then you can say this three events are independent, or more than three, then that many pairs you have to check. Okay. Mm, okay. Maybe we can do this example. So well, okay, so a couple is planning to have three children. Okay, three children, assuming that each child is equally likely to be of either sex, right? So that the sex of children are independent. Find the probability that all three children are girls. Right? So um, Okay, so first child, okay, should be girl, second also girl, and third also girl. Okay, so this is what we have to figure it out. And assuming that each child is equally likely to be of either sex. So here assume that there is a girl and boy. Okay. This true scenario could happen, and we wanted to have all three as girls. So how is it possible? Uh, right. So since they are independent, what we have to figure out, we wanted to figure out that first should be girl, right? First should be girl, and second should be girl, and third should be girl, right? So this we want, and you know that we when we use and we usually multiply, right? G1 multiply P of G2, P of G3, right? But this condition will only hold if G1, G2, and G3 are independent. If they are not going to be independent cases, then I can't do it, right? I can't use this formula if they are dependent. So it is it should be clear to me that they are independent, this G1, G2, and G3, or they should be uh, if they are not independent, then I can't use this formula. This formula will not hold. Thus I have to use like G1, that if G1 was given, then how will I find G2, right? And then multiply it with, let's say, G3 given G1 and G2. Okay, so then I have to use this. But in this case I don't have to use this because it's being said that they are independent, and you know that having first child, then second, then third, there's nothing to do with any. They are not dependent logically, but logically uh mostly it will not work with independent dependence. Like I'll most likely recommend that use mathematically, go with it, and then figure it out. Okay, so mm, you can have this, and since you can have this formula, you can multiply all of them and you will get 1 by 8. Right? It's very easy question, but you should know that they are independent. This part, if it's not known, then this will become very difficult and maybe not solvable. Okay, so we saw how to figure it out what is independent and dependent cases. We'll use this formula, right? If it is equal to um, all of them and each pair of them, then we can say they are independent. If it's independent, then I can use this formula. If it's independent, okay, fine. Uh, Now let's see law of total probability. Uh, this is important. So see, till now we saw what is multiplication rule. Okay, we saw joint and margin probability, but uh, that is okay. You can calculate, but multiplication rule. Remember that. Then based on multiplication rule, we kind of figure out what is independent dependent, right? So that is also important. Now another uh, question comes up is this law of total probability, right? Um, so let's say this a space, and there are several events happening here. Let's say several of them, but they should be exhaustive. I mean, this all events are part of universe, but they all comprise of total of them. So if you sum all of them, let's say E1, E2, E3, E4, and E5, right? So summation of all the probabilities and so on till P of E5 should be equal to 1, right? So this all should include all of them, right? So that's what exhaustive event is. If I write like this, that means it is exhaustive. If you see this word somewhere, be careful. That means all the events have such a way that we have the total probability is equal to 1, right? So if we have this, then we can do something which is related to law of total probability. Um, is okay, fine. Let's see. So you can have this, right? Let's say like this. There's some event happened, another event, okay, which is like this. Okay, this is my event. I'll call this as F. This whole thing. The good part is you can we did it earlier when we checked about this part, right? That uh, what we wrote is we wrote P of E, this E, this F. We wrote P of E is equal to P of um, E given F. That's what we added here. Plus we added P of E when F complement is given, right? So or maybe intersection we can bring it, right? Something this way. Okay. uh, this is what we did. Now same thing we are going to do here. We are going to figure out what is P of F, and what you can do is you can have uh, multiplication of mm, so same way. See, in my diagram it was a little bit different, but if I draw like this, you can say this is F1, this is F2, F3, F4, this is F5, and this is my common E. This is my E here, right? That's how it is. So now if you can see, F1 is given to me, and I want to figure it out E, right? So this part which I'm choosing, or you can say, and then I'll multiply with F1, right? So this part plus same thing I'll do with F2, right? F2 happens, and then will E happens or not, that part, then multiply it with F2, right? So this whole thing you can multiply, and it will be equal to P of E, right? So how will you write P of E is they are happening with several other mutually exclusive events, right? So the one thing is to be make sure that they are mutually exclusive, because if they are not going to mutually exclusive, then you can't figure it out actually. So you can't do that, and there is no way you can do that. So this law of total probability will work when they are mutually exclusive, which they are, right? You can see they are not. The F1 is not going in F2. They are disjoint events, right? So there is nothing common between F1 and F2, right? So this is disjoint. Disjoint is equal to mutually exclusive. So from this, you can actually figure it out what is P of E. You can sum them up, all of them, and this is how you will get the formula final. But this is not recommended. This, remember this, okay? This is far easy, and you know what you have to multiply. Let's say F1 is there, then F2, Fk. So this all mutually exclusive event will be in multiplication, and given that I want to figure it out with the E, right? That's how it goes. Fine. So this is the
Explain it by using question.
yeah. Let's do that. So mm, okay, this question is little okay. Let's see. I'll have another question. Let's say we have three machines. Fine.
Yes, sir.
Okay. Let's say so. It's producing something. Something. Let's say it's producing pens. Okay. Fine. So this will produce. This machine is producing 60% of all the pens. This will produce 30% of all of them. This will produce 10% of all of them. Fine. So that's how I'll have 100% of them, right? This 60, 30, and 10. So that's how I'll get all of them. Now, whatever my first machine is producing, it has some amount of defect, right? So defect is there. Fine. Let's say okay, so
No, you are not audible.
yeah, okay, yeah, sure. Give me a minute.
Oh, okay.
So let's say this yeah, there is some defect in pens, right? So let's say defect is there, and first is let's say 7% defect. Let's say another has 15% defect, and this has 30% defect of total, right? So let's say it producing 10%, and out of 10%, there are 30 which has defects, right? Out of total, I mean, first thing is it is producing 10% of pens, and of the producing pens, it might have 30% defect. Okay, so this is how the question is. Um, now, let's say one pen was selected, right? Then what is the probability that it is defective, right? So that's what my question is. One pen is selected and probability of defective. This is the question. So see if I do, let's say, p of maybe d1 plus d2 and d3, it will not work, right? That's how you can't solve this question. No way, you can't do that, because first I should know how many pen that machine is producing, and I should know how much defective that machine is going to produce, right? So this whole thing I have to figure out, right? So let's say first thing is I am choosing a pen, right? So pen is going to be defective, right? Or if I draw our diagram, let's say this is machine 1, machine 2, this is machine 3, right? Exhaustive event, different machines will not produce same pen, not possible. This will produce 60, this will produce 30, this will produce 10. Fine. This will have 7% effect, this will have 15% effect, this will have 30% effect. Okay. Now I want to figure out is it defective or not. So you can say kind of like this, right? So what I have to do is first I have to select P of machine 1. Is it coming from machine 1 and is it defective? Multiply with it was chosen from machine 1, right? That this is the law of total probability that I have to use.
Okay, sir. Got it.
Then another case I have to go, which is
Machine for machine 2. The same thing will happen.
yes, for machine 2 I have to do that, right? So from machine 2 I'll do again that defective and it's coming from M2, and I'll multiply with probability of M2, right? So first I should also select that it's coming from a machine, one machine, any one, right? One of three.
Yes, sir.
And since they are not equal, I have to include what is it? 60% is producing by M1, then something by M2, and so on. Okay.
Yes, sir. Got it.
Okay. So the last one I'll write, which is your
Defective one M3.
effective, and it's coming from M3, and I'll multiply it
Yeah.
with M3, right? So how many defective M1 was producing? 7%,
7%.
right? Right. So how will I write 7% in terms of probability? 0.07, right? 7 by 100, basically. And what is this? What is the how many pens are produced by M1 machine?
60.
0.6.
0.6, right? So you have to multiply plus how many defective are produced by M2 machine?
0.15.
0.15. And how many pens are it is contributing? 30%.
0.30.
30 plus what is DM3?
Oh,
D given M3, D given M3,
3.6.
0.30,
30 into 0.10.
0.10, right? So if you do this, what is this? 7 into 6, 42, and like this. No, sorry. Okay.
Yes, sir. Got it, sir.
Yeah. So if you multiply
Yes.
all of them, you'll have this probability. Fine.
Yeah, got it. So actually, I'm facing difficulty in implementation of formula.
Yeah. So you understood, right? So see, first
Yeah,
thinking
I
that
understood.
from where it is coming, then what is that part? So that's how you can solve this.
Sir,
And same this question is, but I this is much better in explanation at least. Yes.
sir, my problem in 8.2 and 8.3.
Okay, we'll cover that. So last is base rule. I'll take your question. Okay, fine. Is it fine? So now last part is base rule. What is base rule? And then we're done with the session. We can take your question. Um. Okay. So
A request. Please explain formula by using examples. Yeah, we can connect more with concepts.
yes, we did that, right? So we took example of dependent independent case. We took example of this total low for probability. We
Yes.
did it. So yes, we'll do it for base rule as well. Don't
Oh,
worry.
okay. Thank you, sir.
Okay. So so what is base rule? Basically, it's a P of f given E, right? So that's what we wanted to figure it out, and we know that uh, we know from this, right? The P f intersection E is P of let's take this one only, f given E, then we multiply with P of E, right? This is we know. So from this only we can actually have this one, that what is P of f given that E has already occurred, which is going to be P of f intersection E and divided P of E. The P of E part is good one, is this is what we did we find using total law of probability. Law of probability. You can see this is what we did here, right? So you can see we did this, and that's what we'll use now for our base rule. So base rule is just nothing different, but what we did is we checked. We first know this formula. This formula we know, and then at denominator we'll use total law of probability formula, and we'll make few changes in, let's say, f intersection E, which is uh, so that's what I mentioned earlier, right? That P of E or P of E intersection f is equal to, you can have it two ways. Let's say P of E given f has already occurred, multiply by P of f, or what you can have is P of f E has already occurred and multiply with P of E, right? So that's what actually we are doing. Uh, we started with, so let's see, both we started with this one, right? At at left, maybe you can see, and we have this, right? So now I am going to write this as this one, right? That's what I, you can see same thing, let's say, right? So basically I can write the same formula in two ways, and one thing I'm proving with the another one, right? And this is the total law of probability, and this is how you will have this formula. Okay, expansion of formula. How is this formula is coming? We know how this formula comes, and how we know how this is total law of probability, and this is just another way to write uh, this expansion, right? So that's how we got this base rule, and that's what base told us, like proof wise, and this is total law of probability. Okay, uh, nothing new in this, but let's see how we can use this to solve a question. This we know, right? That's what we already did in total law of probability. Just one thing you have to make sure that they are mutually exclusive and exhaustive. We did same thing there also, right? They were mutually exclusive. There is nothing common in between, and they are exhaustive. So they are exhaustive means this whole thing will combine the probability is one. Okay. If they are not, then we can't use base rule. Um, just so make sure. Mm, okay. So insurance company believes that people can be divided in two classes. So they can divide people in two classes. Those who are prone to accident. So they are prone to, or maybe accident, and those who are not. Okay. Or maybe a complement you can write. The data indicates that accident prone person will have an accident in 1 year period with probability of, so this whoever is accident prone um, will have accident in 1 year period. So we are now choosing 1 year period, okay, with probability of 0.1. So 0.1 that it will happen in 1 year. What another case could be that it will happen in more than 1 year. Okay, so more than 1 year is 0.9, not 2 years, but more than 1 year. Complement of this. Okay, uh, that's how you have to see. Then another side, if you go, the probability for all others Probability for all others is 0.05. Sorry,
Probability for other years is 0.05, na sir?
for all others, but hmm, uh, okay. Suppose that the probability is 0.2, or maybe they are saying that E given F complement, and F is accident prone. So accident prone is a given F complement. So who is not accident prone? Not accident prone, which is this, is 0.05. Yeah, see, this is what 0.05. If I am understanding right. So this is actually 0.9, which is not much important to us for solving this question, but like this. So this is how this distribution is going on. Okay. Okay. Now suppose that the probability is 0.2 that a new policyholder is accident prone. Suppose that this is given to us 0.2. Okay, so that new policyholder will come someone. So choosing this is 0.2. So actually you can see this is 0.2 is 0.8. Okay, you can maybe a new policyholder. I think that's what the yes, right. So yeah. So if a new policyholder has an accident in first year, what is the probability that he or she is accident prone, right? So somebody who has accident in first year of the period, okay, and are they so one is they could be accident prone people, okay, or they are not, right? So not, so they are coming from any of one of them, either this or that. And if so now they're saying the rule is probably that he or she what they given us is that a new policy holder has an accident in first year itself. So somebody who got a policy, he met an accident in first year itself. So what is probably that he or she is from this subset, right? So accident prone, correct? So we have to solve this. So how will you do that? So given to us is, or if we see our base rule, let's see, we just now went through it. So this is the part we okay. So we have to figure it out what is probability of somebody who met accident, right? Met in first year, yeah. So sorry, first year. Now he's from this accident prone subset, right? So this is what I want to figure it out. So how will I do is I will write this like E of first I need to figure out what is probably E given F, right? Which is opposite of this F given E. So I mean, so what I need to find out is he is from first year and he had accident that I need to figure it out, correct? And then I have to multiply it with probability of accident. Okay. And in the division I have to do same thing using my total law of probability that uh, So here two cases are there. He could have accident and not accident, and then something subset, right? So is he coming from? Is he met in first year? Sorry, first year. All the first year who are in accident or non-accident, right? So accident, non-accident, first year one. That I have to figure it out. So that I'll do using this, that somebody F accident, right? P of say, first year given accident, and then multiplication with P of not accident. So I'll say not accident, and then multiplication with P of first, given that it's from not accident, right? So this formula you have to solve and then figure it out. Okay. This question itself is a little difficult, but that's all. So how will you do that? So we know okay, what are the things we know? What is the probability of having accident is 0.2 in denominator, right? In denominator, if we know that having accident is 0.2, and if somebody has met accident and he is in first year, in first year, that is going to be 0.1, right? That this also we know. So 0.2 into 0.1. Then I'll multiply what is a complement, which is not having accident. That is going to be 0.8. From this diagram also you can see. And so in that somebody is from first year, which is 0.05, right? So this how this will play out, and you'll have this as denominator. Now we want to figure out what is in the numerator. Somebody who had accident and he's in first year, actually we already figured this out. This is 0.1, correct? So who met accident and he's from first year is 0.1, and probability of going through accident is 0.2, right? So to wait, this multiplication, no, this is going to be addition, this is going to be addition, this part. So otherwise we would have just cancelled it, right? Nothing would have changed. And from this you can have, so this is going to be 0.06. At top also you will have 0.02. From this you will have that is 1 by 3. Okay. Yeah, 1 by 3. So whenever this kind of question comes up, I recommend that you draw this tree. You can call it tree or something. But if you draw this tree, then you'll most likely able to solve this question. Okay. Just you need to figure out which part is which one, and then you can solve it. Don't use Venn diagram for this. I mean, if you are proficient in that, you can do that. I'm not saying anything. But in this type of question, when this something is given and then something will happen, that kind of question may, if you solve using trees, it will help. It's far easy to draw this. Okay, and that's what the base rule is. You can remember it also, like this is the base rule.
Excuse me, sir.
Yes.
Sir, I have a doubt. When will you start revision session for quiz 2?
Was this next to next week? Right?
After 1 week, sir.
Next, yes, after next 1 week.
Yeah, okay, sir. Thank you.
Okay, so who has doubt in any activity or something? Somebody is asking. We can take that.
Sir, yes, sir. We didn't actually submit the quiz, last two extra activities, sir.
1 and 2.
Yes, sir.
Why?
Actually, I don't have time to do that thing, sir.
Okay.
So can I submit the third activity, sir?
Yeah, sure, you can do that. I mean,
How many marks, like extra marks, will I get, sir?
I'm not sure about that. You can check the reading document how much you will get from that. Yeah, I don't recall actually. Mm, So anybody has question in activity question that you need to take me now? Because Tuesday we'll take all of them. So nothing else we can drop.
So where can we find a video on activity 3, sir?
There's no video on activity 3. Whatever. So video was there to demonstrate how to submit it, right? And submission you have to do uh, by yourself. I mean, you have to solve that question, whatever is there.
Yeah. Okay.
So you'll have bonus marks extra 5, right? So cap to 5. So you'll have 5 of that. I mean, there are 4 activities actually. So one activity carries 1.25 marks. So you didn't submit 2, so you'll have out of 2.5, whatever you get.
Thank you, sir.
Okay, so you can see 1.25 marks each here it's mentioned. Okay. Okay, so thank you all. We can close the session.